The delicate balance of a wetland environment. A world where each citizen is eager to participate in the circle of life. Take the female mosquito, for example. In preparation for laying her eggs, she feeds on blood, creating nuisance and spreading disease. Yet her offspring, the mosquito larvae, feed on organic material, including bacteria that are found in these aquatic habitats. This makes it possible for two naturally occurring bacteria, Bacillus thuringiensis israeliensis and Bacillus sphaericus, to provide environmentally compatible mosquito control. These bacteria are quite appetizing to the larvae until they attack the larvae's digestive system with a special protein they produce. And so it goes for the life cycle of the mosquito larvae, over before it has even begun. By using BTI and B. sphaericus to combat mosquito infestation, modern science is taking advantage of one of the fundamental laws of the animal kingdom. The most effective solution is the natural solution. Most mosquito control programs use one or more standard techniques to reduce the local mosquito population. Source reduction involves the complete or partial drainage of larval mosquito habitats. Adulticides are chemical pesticides used to reduce existing populations of adult mosquitoes that could cause disease outbreaks, while larvicides suppress mosquito populations in the larval stage, before they can become biting adult disease carriers that can disperse into residential areas. Out of all these mosquito abatement methods, biological larvicides are usually the most cost-effective, efficient, and natural solution. Biological larvicides are appealing to mosquito abatement districts and public health departments for several reasons. Since biological larvicides are specific in suppressing mosquito and black fly larvae, these products are acceptable alternatives for mosquito control because they minimize the potential of toxicity for humans and wildlife. Biological larvicides are 95 to 100% effective in virtually all mosquito habitats when properly applied at the recommended rates. And using these products reduces the need for widespread chemical fogging, making biological larvicides a very economical solution. Before using biological larvicides, it is important to have a clear understanding of how they work. The active ingredient in biological larvicides is either BTI or B. sphaericus, two naturally occurring bacteria. After the larvae ingest these organisms, protein crystals from the bacteria are activated and rapidly destroy the mosquito larvae's digestive tract. The larvae are dead within 48 hours of ingesting the bacteria, before they can develop into biting adult mosquitoes that could spread diseases such as West Nile virus. Unlike chemical larvicides that kill on contact, biological larvicides have to be ingested by the mosquito larvae in order to be effective. And since BTI and B. sphaericus are so specific, it is important to survey the larval populations and their habitat to determine which biological larvicide is best to use and when to use it. BTI is effective against virtually all mosquito species. The success of any biological larviciding program requires that the following steps are handled properly for each application. Surveying the larval populations, timing the treatments, selecting the larvicide product, selecting the formulation, selecting the usage rates, mixing and calibration, distributing the material and covering the treatment area, and monitoring the area for efficacy. Mosquito larvae develop in still or slow-moving water. Their habitat can be as small as a pail or as large as a rice field. Most habitats and water sources can be surveyed with the standard mosquito dipper. When performing mosquito larvae surveillance, it is important to determine where and when there will be large concentrations of larvae. Knowing the larvae's stage of development will also dictate the proper timing of the treatments. Newly hatched mosquito larvae will remain in standing water for a period of 4 to 21 days. Their feeding activity is greatest during the early stages of development, from the first instar through the third instar. This window of opportunity is the best time to apply biological larvicides. BTI and B. sphaericus will no longer be effective once the larvae stop feeding, by the latter part of the fourth instar. Also keep in mind that certain types of mosquitoes have broods that hatch and develop at the same time, while other species might stagger the timing of their egg hatch, requiring multiple treatments. The timing of the initial treatments will be less important if the larval development is staggered, such as with Culex mosquitoes. The follow-up treatment should be made when new larvae reach the early 4th instar. Once the location of the larvae and the timing of the application have been determined, it is time to select the appropriate larvicide formulation. The formulations applied as liquids, when applied correctly, provide complete coverage in the sprayed area. Granular formulations work best where there are dense vegetative canopies that cannot be penetrated by liquid sprays. A granule formulation offers more granules per square foot and provides the best coverage in small, isolated pockets of standing water, requiring more point sources. BTI is most useful as a broad-spectrum larvicide with short-term residual effects. In bodies of natural water, the larvicidal effect of BTI will normally last only 48 hours. However, in small artificial containers, the effects can persist for more than 30 days. BTI is most effective with the following species and habitats: single brood Aedes and Ocleritatis in salt marshes, floodwaters, and pastures, container breeding Aedes, and other areas where the initial cost of treatment is more important than the residual control. Use the lower application rates when there is cleaner water, low larval populations, and earlier instars. Higher application rates should be used for polluted water, high larval populations, later instars. Following the instructions on the product label, each mosquito control program will have to select rates based on their specific situation. It is also important to properly mix and apply BTI according to the label instructions. WDG, water dispersible granule formulations, mix readily with water. When mixing the WDG, it is important to add water to the tank first. Before adding the WDG formulation, then agitate the tank well prior to application. The directions for diluting the formulation will differ between ground spraying and aerial application. Refer to the product label for this information. Calibration is a simple but essential step to ensure that the proper larvicide dosage is applied to the larval habitat. To properly calibrate your application equipment, you will need a stopwatch and a container to collect the product being expelled from the equipment. Determine the amount of product being applied as gallons per minute for liquid applications or pounds per minute for granular applications. You must then determine the speed at which you will be traveling and the swath width you will be treating. Application rate equals flow rate times 495 divided by speed times swath width. Flow rate equals application rate times speed times swath divided by 495. The appropriate application rate needed for your treatment area can be determined from the product label. If necessary, you may have to adjust your equipment to either increase or decrease your time flow rate in order to produce the desired application rate. The dosage amount will be determined by the travel speed of the applicator, width of the area covered, and material flow rate. The larvicide must also be distributed as evenly as possible, with full coverage of the treatment area. BTI are water-soluble, and the bacteria do not spread out on the surface of the water like oils or certain chemicals. At the point of distribution, the active proteins in the biological larvicide settle into the water column. Mosquito larvae that are already feeding there will ingest the active proteins and die as a result. However, if any area is left untreated, it is highly unlikely that the larvicide will travel to that location. Any larvae in an untreated area will probably survive, so it is critical that there is even distribution and full coverage. Monitoring the treatment area for efficacy will ensure that the biological larvicide program is working. Areas treated with BTI should be sampled 24 hours after the initial application. Larval development might resume 3 or 4 days after treatment, but it is not necessary to retreat immediately. To maximize the efficiency, it is best to wait until the larvae reach the later instars before treating the area again. For rapidly developing Aedes, retreatment should take place in the 3rd instar, and for Culex, retreatment can wait until early 4th instar. This will allow for a 7 to 14-day treatment schedule. What was once a breeding ground for airborne disease carriers is now a graveyard for mosquito larvae. And it was all made possible by helping nature take its course. Mosquitoes will never lose their instinctive urge to breed or their natural desire to feed. It's time that we learn something from the animal kingdom. By using biological larvicides to reduce the mosquito population, mosquito control programs can alleviate their mosquito problems and restore the delicate balance of nature.